All right. Any questions before we get going? Okay, Anthony, go ahead.
I had a question on the first question problem, on how to get the slow portion of the
Okay. So slope, you have to calculate the slope, and it gives you the head loss or the difference in the reservoirs, right?
Difference in pressure.
It gives you difference in pressure. Oh, this is great. Great question, because that will lead us right into what we're going in today. And so this is something you know, but you don't know that you know. All right, so let's kind of bring this in. Okay, so in fluids, often we work with simplified systems to help us grasp the concept, all right? So a lot of times, and we're going to do it today, we're going to have two reservoirs that are connected, and each of them has a water surface elevation. There's our water surface elevation, okay? And hopefully we understand the concept. Well, let me ask you guys, what drives the flow? Gravity differential, yeah. So we have a head differential or an energy differential between those two, right? So here's another concept question. You're down at your favorite, fast food place, McDonald's or wherever, sucking on your favorite soda. Is the soda being drawn into your mouth, or is it being pushed into your mouth?
Pushed.
I just want it in my mouth, right? And Aaron says it's being pushed. Can you explain that in a little more detail?
So we're reducing the pressure inside the straw, so the pressure outside, the atmospheric pressure, is pushing that fluid up into the straw or into our mouth.
Okay, good. Okay. So fluid flow always occurs from high energy to low energy. And when you create a vacuum in your mouth, you just created low energy. And that's why the atmosphere then pushes it into your mouth. Okay. And heat is the same way. Heat flows from high energy to low energy. So if you have ice cubes in your hand, it's not that the cold is flowing out of the ice cube, it's that the heat is flowing out of your body into the ice. Right? And you may say, well, does that matter? Well, for most things, no, but there is for some things that it does make a difference. So in this particular problem, we have gravity that's pushing that, but we're going to let gravity represent simply an energy potential, if you will, okay? Because we're going to use the Bernoulli equation and say P1 over gamma plus P plus Z1 plus V1 squared over 2G down on this end, and P2 over gamma plus Z2 plus V2 squared over this end, all right? And because we're going to assume that there's relatively no flow in those tanks, it's all in the pipeline, we can say that the velocity goes to 0. And if we put our datum right here, Z is equal to 0. Now, it's very possible that our reservoirs may be at different elevations. One could be up on a hill and the other one's down low. And that's fine. Because we just don't turn them into 0 then. We just put what the respective elevations are. But from that point, you can see that if we just call that 0 to simplify the life and our life and answer Anthony's question here, what we're left with is a pressure head at point 1 and a pressure head at point 2. If you know the fluid that is flowing, water, and you know the pressure at one point and the pressure at the other point, can you find the respective differential in those two flows? Does that answer your question then? Okay, let's, if it doesn't, let's keep going here. Does part of it not make sense? Where are we at?
No, I think
Okay, so give me the values from the problem. What's the pressure at point 1? At the
60 psi, and then the final.
And the final one's what? 53, okay. So p sub 1 equals 60 and p sub 2 equals 50 psi, okay? And so now if we want to know, if we want to say, okay, rather than having a pressure, let's turn this into an elevation, if you will, or a length, hence the term head, right? Pressure head, velocity head. So what we're going to do then is we're going to say that the water surface elevation is equal to the pressure head at 1, which is going to be equal to 60 pounds per square inch. And we have to do a little bit of conversion here. We know there's a sorry, okay. There we go. Okay, that pen's not working so well, but we know that there's 144 inches squared in 1 square foot, and gamma is 62.4 pounds per cubic foot. Okay, so when we do this, the inches cancel out, the feet squared cancels out with the feet cubed down there, the pounds cancel out, and that feet on the bottom comes up to the top, and that equals some value in feet. And when we do the same thing for tank 2, now we have essentially the water surface elevation of each of our tanks. Okay? All right. Any additional questions? Okay, so we're going to jump to jump over to the energy equation. Whoops, that's equation right there. Energy equation with Darcy-Weisbach. And if I remember my history correctly, these are two different people that came up with the equation independent of each other and within a few years of each other, you know, back in the days when there wasn't a lot of communication. So they just gave them both the name of it. So the energy equation with the Darcy-Weisbach for friction loss. Okay, where this says that the friction loss is equal to F times L over D times V squared over 2G, or continuity, and we substitute Q is equal to VA, or V is equal to Q divided by A, then we can turn this into F times L over D times Q squared divided by 2G A squared. So either one of those works fine for calculating the friction loss in a pipe. We tend to use the second one because we often want to know what the flow rate is more than the velocity. So now where we had the Hazen-Williams on Wednesday that we talked about, we can look at the flow rate or the velocity. We can look at the head loss using the Hazen-Williams. Now we have another tool that does the exact same thing. This one is more physics-based. Came from a dimensional analysis. It is dimensionally homogeneous, or the Hazen-Williams has that correction coefficient, okay, or the conversion coefficient. So this one is better, in my opinion, and just because it's founded on those physics principles, and it works really well, with the exception, and this is true for the Hazen-Williams as well. Have I told you guys about large diameter pipes? I don't think I did.
How it doesn't apply as well.
Yeah, it doesn't apply as well, and we started talking about Ted Sorensen in here, didn't we? Okay, so this came out of a conversation with him as well. That's why I was thinking maybe I told you guys, but what did I bring him up before? Can't even remember. It doesn't matter. Or Scott, did we talk about large diameter pipes?
Yeah, you just mentioned that you didn't know why people still use the Hazen-Williams.
Oh.
Because it doesn't apply for everything, and it's just an old and archaic system you don't prefer.
Yeah. Okay, thanks. That's a nice summary. So Ted uses the Hazen-Williams, and once again, it works for him. All right, and he's been very successful. He puts in these large ones. Some of them are small too, but he's got all these power plants, and he has one power plant where he has an 11-foot pipe that's bringing the water down to the turbine. 11-foot pipe. Okay, it's huge, right? Move a lot of water through 11 feet. And in our discussion, he said, you know, the equation breaks down. And And I was like, well, which equation? He said, Hayes and Williams. And I said, you try the Darcy-Weisbach? And he said, no, I don't do that. So I looked at it, it breaks down too. Well, when I say breaks down, the Darcy-Weisbach predicted pretty close to the Hayes and Williams. And so I started doing a little digging. Turns out this is a well-known phenomenon, and I'd heard it in the past, I didn't remember much about it, that large diameter pipes have less friction than predicted. And what are we talking about large? Well, that could be a 4 foot, a 6 foot, or whatever. And sometimes the difference is very small, especially if you have a lot of elbows and bends. But if you have a long straight pipe, the theory breaks down. Does that mean our theory's wrong? Well, yeah, it does, doesn't it? It means there's something going on that we're not accounting for. When we did a dimensional analysis in fluids, when we did the modeling, the pi theorem, Buckingham pi theorem, there's something we missed. Otherwise, the equation should work correctly. And it's interesting to note, this just came out a few years ago, maybe 10. I think it was over in England. They did an experiment where they took a 1 foot pipe, not huge, but a 1 foot pipe that's, decent size, and they rotated the pipe while the flow was going through it. So in other words, the pipe spun. And guess what? It reduced the friction loss in the pipe. It's like, that's weird. Why would a spinning pipe, you would think that would have more because now the wall is moving, right? And it's not like it's translating with the flow, it's spinning around. And so they started tracking the flow vortices in there, and they found that when you do that, you get these little tiny vortices that build up around the perimeter of the pipe. And that actually, in their estimation, their calculation, they said that's what causes or allows the flow to go through there easier than if it wasn't there. And so people, and no one to my knowledge has proven this, but they hypothesized that large diameter pipes, because they are so big and it's a large area compared to a relatively small surface that the flow is going through, that they also somehow set those vortices up on their own and bring the flow down. Because Ted's saying, if I would have known this, I could have put in a 9 foot pipe rather than an 11 foot pipe, and it would have saved me a lot of money. I had a little more loss, but that's not, the $500,000 that he put out on the larger pipe could have saved some money. Okay, so it's an interesting phenomenon. So where are we at here? So in spite of that, there's not many people put in 9, 10 foot, 11 foot pipes. So this works really good for what we're doing. It works really good. 2, 3, 4 foot pipes. And now we can then calculate this right here, but we need to find this friction factor. All right. Remember from fluids how to find the friction factor? There's a couple of ways.
Moody diagram.
Moody diagram is one, okay? So we've noted that the friction factor is a function of E over D and the Reynolds number, okay? And one way is to use the Moody diagram. Okay? And the book here in chapter 4, we can crank that open to the Moody diagram. Okay? Well, there's the Moody diagram. A couple of things we need to be aware of the Moody diagram is that over here on the right, we have the relative roughness, K sub S, which is also E, to equivalent sand roughness, or epsilon. We use all three of those variables, little e, epsilon, and K sub S, sand roughness. We divide that by D. So the roughness is in feet or in meters. D is in feet or meters, so it's dimensionless. It's a dimensionless parameter. And then we have the Reynolds number down here, which is also a dimensionless parameter. Okay. So if I have a Reynolds number of, say, 1 times 10 to the 5th. No, let's do this a little different because I want to make sure you understand this. So 1 times 10 to the 5th. Yeah, 1 times 10 to the 5th and an E over D of 0.001. What is my friction factor? Give or take. So, best you can. Let me see if I can zoom that out a little bit. Oh, a little too far. And I know reading it from there, it's going to be hard, but you should be able to get kind of close, right?
0.022.
0.022. Okay, that's probably in the ballpark. Anyone down here? Wyatt, what do you think?
I got more like 0.02, but it's hard to.
Yeah, it's hard. Okay, so let's look at this. 1.1 times 10 to the fifth is on this line right here. So I'm going to follow that up. And then right here, 0.001, I'm going to follow this over. And even after it curves, I'm going to follow it. And when those two intersect, then I'm going to bring that across. And I'd probably say 0.023, but you know, without having a straight edge, it's pretty tough. And it's even tougher up there. Okay. So a couple key things you should remember from fluids class is that you follow E over D until you intersect with the Reynolds number. And then you go horizontal. Okay. Now I like to ask, find the friction factor on a test. That's a big hint right there. So be aware of how to use the Moody diagram. All right. Over here on the left-hand side, we have typical values for relative roughnesses. And of course, we looked at on Wednesday a little bit more. I think that was back in chapter 12, where there's a better list than this. All right, but that's where we can find E, and we know that if we know the diameter, then we go ahead and use that. Interesting story about the Moody diagram. All right. There was two guys that came up. They took Nicarossi. Remember Nicarossi? He was the guy that put the sand inside the pipe, and these two guys, Colebrook and White, they took Nicarassi's data and they said, yeah, we think we can graph that. Okay. So took Nicarassi's data, and Colebrook and White came up with this equation right here. And they said that 1 over the square root of the friction factor F is equal to -2 times log base 10 of the quantity E divided by 3.7 times D plus 2.51 divided by the Reynolds number times the square root of F and the quantity. And they said, using that equation right there, you can find the friction factor. Oh, sure. Yeah, I can do that. Yeah, thank you for back out. So I don't do that again. Okay, there we go. Okay. Anyone see any problems with that equation? If I asked you to find the friction factor F, Scott, what would be the problem?
You'd have to guess on the first factor and try and go from there.
Yeah, yeah. You have it on, the friction factor F is on both sides, and you cannot solve this equation where the friction factor is only on one side. If you do, bring it to me, we'll both be famous, right? Because that would be pretty cool. It's what we call an implicit equation. You can't separate it. Now we can solve it numerically, so it's not beyond our reach of solving it. Like Aaron noted that you can take a guess and you can cycle through this and find it. But back pre-computer days, that was pretty tough, right? So Nicarossi did the sand data. Holbrook and White, they took the data. How'd they come up with this equation? You know, before computers. I mean, what are they sitting around smoking going, dude, if we did this, it would plot, you know, it's like, how do you come up with that? But they did. I mean, it makes my mind, right? They verified that it works, but no one could use it, or it was really tough to use. And so some other people started coming up with some different equations. And there's, if you get on Wikipedia, you'll find like 20 different equations. The Wood equation, blah, blah, blah. Some are better than others. Some only work in certain ranges. Back in the 1940s, there's a guy named Hunter Rouse. Okay, now Hunter Rouse, if you get into my field in fluid mechanics and hydraulics, he's very famous for what he did. I mean, the guy was brilliant, and apparently he had the ego to go along with it. And he was presenting at some conference, and he had a graph that would show the Colebrook-White data. And he was up there explaining how the graph worked. And well, there was a graduate student in the audience, not from his institution, from a different institution, went up to him and said, you know, Professor Rouse, if you did this and moved this over here and moved that up there, I think that would clean up your graph a lot and make it a lot easier to understand. And Hunter Rouse said, stupid idiot, who's the professor here and who's the student? So Moody went back to his institution, looked at it, said, I think I can do that. Plotted it up, every basic fluids book now has a Moody diagram in it, and you won't find a reference to Hunter Rouse. So I mean, it's kind of ironic, right? I mean, Hunter Rouse, you get farther in the literature, you find them all over the place, but basic fluids, not there. But Moody diagram, all he did was plot this equation onto this graph right here. That's what he did right there. And plotted that up. A student today with Excel, and if you know what you're doing, you can do that in 2 hours. But back in his day, that was a lot of work, and rightfully so. He had the graph named for him, and you're in fluids, you know about the Moody diagram. Okay, now the Moody diagram's great, it's nice, but if you're writing a program, it doesn't work so well. It's pretty hard to put a graph in there. You can put charts and charts and charts, but still, it's not the greatest. Some other people have tried to come up with ways of finding the friction factor. And there's two equations out there, the Holland equation and the Swami-Jain equation, that both work pretty good. And I like the Swami-Jain just because that's a cool name. And I think it's gotten a little more traction than the Holland equation. So the Swami-Jain equation is this. There's two forms of it. So right here. So F is equal to 1.325 divided by the quantity, the natural log of the quantity E over 3.7 times D plus 5.74 over the Reynolds number raised to the 0.9, end of quantity squared. Okay. Or if you prefer log base 10, we have that equation too, where the friction factor is equal to 0.25 divided by then the quantity log base 10 of E divided by 3.7D. It's the same inside stuff here, plus 5.74 divided by the Reynolds number raised to the 0.9, end of quantity squared. So whichever one you prefer, the natural log or the log, you can use that. Okay. So now we have both a diagram and an equation and it's not perfect. It's not exactly the Colbert-White, but it's pretty close and it's within the tolerance that we can guess. You know, we're getting E over D and we could be off on that. So Swami-Jain works really nice. And because the friction factor is explicit, it's been solved for the friction factor, it falls right out, right? So it's easier to program. Okay, so now with these tools in our hand, we can now solve single pipe flows. So single pipe flows, we have a couple of different ways of doing that, or a couple things we can do with this. We can solve for the flow rate. We can solve for the head loss. And we can solve for we can design for size, diameter. Okay. Now we can do other things with the Darcy-Weisbach equation and the energy equation. We could solve for E, the roughness height for a pipe, but that's more on the research side. So we want to know, how do we use this out in industry? Okay, so we're going to look at these three different cases, and let's start with the known flow rate. All right. Sorry. Let's do that. I should have put number 2 first. Let's start with that one, the head loss. How do we find the head loss? So let's work an example. Sorry? Someone has their mic on, just letting you know. Okay. So find head loss. So if we were looking at this as in terms of a simple example, essentially what we're saying is that, oh, I'm going to put a little note up here, neglect minor losses. Because we haven't got to those with, I mean, we've talked about them briefly, but we're going to go in more detail. So we're saying, what we're saying here is we have a system of two reservoirs, okay? And the question that Anthony asked us about, well, how do pressures relate? Beautiful. I mean, that just led right into this, because once again, these reservoirs are symbolic, they're representative of the total energy. You know, so I'll have to send you a check later for asking that question, but it's great to point out the fact that we can have pipe pressures, we can have elevation changes, we can have reservoirs like this, we can have pumps, and we're going to add pumps later on, and we just convert them into a representation of the energy. So in this particular scenario, we know that we have a flow going through here, but we don't know, and we know the flow rate. So let's say Q is equal to, I don't know, 8 cubic feet per second. Okay. We're going to say the length of our pipe is 2,500 feet long. And we're going to say the diameter is 8 inches. All right. And we're going to say that the relative roughness height is 0.0. Well, let's see. Let's look at what we have here. Let's get a good value. So I'm going to come up here for, let's say, steel pipe. Okay, and we're going to do this in feet. So 1.5 times 10 to the fourth, and that's in feet. So 0.00015 feet. And we're going to say the viscosity of water, 1.41 times 10 to the negative 5 feet squared per second. That's kinematic viscosity of water at 50 degrees. Okay. So we know that we have this flow going through that pipe, but what we don't know, let's say we know the bottom reservoir elevation here of 100 feet, and we want to know what is needed to produce that flow rate. So in other words, what is the head loss in our system? Because if we know the head loss, that's how much additional energy we need to push the flow through there, right? So now that we have this, we can just say, all right, well, let's go ahead and write 0.1 right here. We're going to write 0.2 over here. And we're going to write our energy equation, P sub 1 over gamma plus Z sub 1 plus V sub 1 squared over 2G plus or minus the mechanical energy is equal to P sub 2 over gamma plus Z sub 2 plus V sub 2 squared over 2G plus then the head loss, but because we're only worried about the friction loss, I'm going to just put that in there, F times L over D times Q squared divided by 2G A squared. Okay. So there is no pump or turbine. So we can go ahead and take that out right there. Much better. Yeah, let's go back to the same color then. Okay, so there's no pump or turbine, and for the next couple of class periods, I'm probably just going to drop that when I write the equation. All right, because we know it's not there. What's the velocity in each of those tanks?
0.1, 0.2.
Okay, 0.1, 0.2. Yeah, so we said it's 0 because the tank is large enough that we're not pulling out so much flow, the level's changing rapidly. Over time, yeah, the level's going to change if we're not adding, but it's so small right now that we're just going to assume that it's 0. Now we don't have to assume it's 0, we can still solve the problem, but it just makes life easy. And once again, if we call our datum down here, Z is equal to 0, that's where we measured our elevation off of, then we can say that the elevation of 2 is 100, and the elevation of 1 we don't know. What about the pressures in each of these?
0. Absolutely.
0 on each one of these as well, yeah, okay. Okay, so now we just need to solve for this over here. We need to find a friction factor. How do we find a friction factor? Well, we know from the Moody diagram that if we have E over D and the Reynolds number, we can find the friction factor, right? So the Reynolds number, well, let's do E over D. So E over D. E over D then is going to be 0.00015 divided by 8 inches divided by 12 inches, because I have to be consistent and make sure that I put my units in the right form, so that is dimensionless. Okay. And so now when I calculate this, it's going to be 0.00023. All right, essentially, we're going to have to do a little bit of interpolating here. And then the Reynolds number, we know that the Reynolds number is equal to the velocity times the diameter divided by the kinematic viscosity. I don't know the velocity, I know the area, so I could solve it. Or I could just convert this equation over and say that V is equal to Q divided by A. So this is Q times the diameter divided by the area, and the area is pi divided by 4 d squared times the kinematic viscosity. If I wanted to simplify that, I could bring the 4 up to the top. So this would become 4qd divided by pi. And the d's are going to cancel out, right? It's going to leave me d down here. So 4q divided by pi d times nu, the kinematic viscosity. So that's just simplifying the equation for the Reynolds number. So now we can go ahead and calculate the Reynolds number. Okay, so Reynolds number then is going to be equal to 4 times 8 CFS divided by pi times 8 divided by 12 times the kinematic viscosity, which I said is 1.41 times 10 to the negative 5. And we know the Reynolds number is dimensionless, so all the dimensions go out. So if I've done this correctly, I get 1.1, I'm kind of rounding it up, times 10 to the 6th. Okay, so let me just do a quick check here. Yep. Okay, good. So now that I have the Reynolds number and I have E over D, I can come back over to the Moody diagram. Okay. And so I'm going to come over here, let's see, how many zeros did I have? I had for E over D, 3 zeros? Yeah, 3 zeros. Okay, thank you. So 3 zeros and a 2. So I'm going to come over here, and that's essentially close enough. And 1 times 10 to the 6 is right here. So I'm going to follow that over. And where that intersects is about 0.015, right? Let me see if I brought my right calculator today. No, I didn't. One of my calculators, one of the two, has a little card in it that has the Moody diagram built into it. 1992, before many of you were even born. But your calculator doesn't have that, right? So my little jab there for HP calculators. So anyway, we're going to assume that we can read that really good, or we plug it into the equation, and we'll call it 0.015, all right? So we're going to let F equal 0.015. So now, come over here, and essentially what I'm saying, I'm going to say that Z sub 2 is equal to 100 plus F, which is 0.015 times L over D. So here's 2,500 divided by D, which is 8 inches divided by 12. Once again, converted to the standard unit of feet, times then the flow rate, which is 8 CFS squared, divided by 2G, times then the area, and the area is pi divided by 4, times D squared, so 8 divided by 12 squared, and the quantity squared. And that there is my velocity head in terms of the flow rate. Okay. Well, that doesn't seem right. Oh, I'm trying to push 8 cubic feet per second through an 8-inch pipe. Okay. Let me verify my numbers here. Because, yeah, that's probably is correct. Oh, it's a little better. Not much. Yeah, that's right. I'm getting the value of, oops, that's not Z sub 2, it should be Z sub 1. Z sub 1 is equal to 458.8 feet.
Did you already add the 100?
Yes. Yes, sorry, I have a, oh, I'm sorry, I didn't, did I? 500. Thank you. 558.8. So in other words, I need almost 460 feet of flow to push 8 cubic feet per second through an 8-inch pipe that distance. I was like, wow, that's a lot of feet. And it is, because an 8-inch pipe, 8 cubic feet per second through an 8-inch pipe is a lot of water. 8-inch flow through a 12-inch pipe would be a little more reasonable. And if we drop that down to 1 foot rather than 8-inch, we would see that that would be significantly less. It would be maybe drop down to like maybe 30 or 40 feet. Okay. Any questions on that? Okay, so let's do condition number 1 then, which was find the flow rate. All right. So now we want to find flow rate. Let's kind of set up the same thing here. A little reservoir. Okay. And we'll say that the downstream one is 100 feet, and we'll say the upstream one is 145 feet. So let's see how close I am to my guess here. And so now we're going to say the length is the same thing, 2,500 feet. Diameter is equal to 1 foot. And kinetic viscosity is 1.41 times 10 to the negative fifth. And the equivalent sand roughness is 0.0000015, commercial steel, like we had before. So it's the same thing as the other problem, except for now our reservoir elevations have changed, and we're dealing with a 1 foot pipe, not a 8-inch pipe. And we want to find now the flow rate. So the goal is to find the flow rate. Okay. So we have the same equation set up. P sub 1 over gamma plus Z sub 1 plus V sub 1 squared over 2G is equal to P sub 2 over gamma plus Z sub 2 plus V sub 2 squared over 2G plus F times L over D times Q squared divided by 2G A squared. Okay, now in the interest of time, I'm going to fly through this pretty fast. We're going to put 0.1 over the first reservoir, 0.2 over the second one. As before, all the pressures go to 0, all the velocities go to 0. V sub 1 goes to 145. Z sub 2 goes to 100. So in the end, I end up with 45 feet is equal to F times 2,500 divided by 1 times Q squared divided by 2G, and then my area then is going to be pi divided by 4, 1 squared, end of quantity squared. Okay. So just simplified our life there a little bit. Put the values in, and we're looking at this equation now. We're going, wait a second, we have two unknowns, friction and flow rate. But that's okay, right? Because I know how to find the friction factor. I just used the Moody diagram. Scott, you're shaking your head. Why?
We need the flow rate to know the Reynolds number.
Yeah, we don't have the flow rate. If we don't have the flow rate, we can't get the Reynolds number. If we can't find the Reynolds number, we can't get the friction factor. No friction factor, no flow rate. So we're stuck. Except for, fortunately, this equation right here is what we call, it's, I don't know, convergence dominant or something like that. I can't remember the math terms, which means that if we start with a reasonable guess, actually even a wildly wrong guess, it's going to converge. This is like a parabola, okay? Even if you start way out here and you're trying to find the minimum, you're going to come down this direction and eventually hit it. And if you start out here, you're going to hit it. So that equation has that form where it's going to converge. So we have to start with a guess. We can start with a guess for a flow rate. We can start with a guess for a friction factor. Doesn't matter. I prefer to start with a friction factor. Okay, it's just what I've learned, because to me it's a smaller range than just wild flow rate. So I'm going to guess friction factor, say 0.02. I know that it's still pipe. I know that this is going to put me in, looking at the Moody diagram, this is going to put me in the range where most of the friction factors are going to be. Okay, so now I'm going to create just a little chart here, if you will. Friction factor 0.02, and then if I know the friction factor, I can calculate the flow rate, and then if I know the flow rate, I can find then the Reynolds number. Now I would note that I still need E over D, but that's a little easier too, because E over D is 0.0015 divided by 1, which of course then is 0.00015. Okay. I'm also going to simplify my equation a little bit, because what we're going to do here is iterate. So I'm going to crank out all these numbers to simplify my equation. So 2,500 divided by 1, and then divide that by 2G times the area, pi divided by 4, times 1 squared, quantity squared, and divide that in there. So if I've done my math right, this whole equation right here boils down to 45 feet is equal to F times 62.93 times Q squared. Now you could simplify that more if you wanted to. But, you know,
Isn't that 145?
It is 145 over here. It's a good question. But remember that my other reservoir is 100 feet. So when I brought that over to this side, the difference between them is 145.
Oh, okay, I missed that part. Sorry.
Well, yeah, that's fine. I'm glad you asked, because yeah, if you missed that, you're like, where'd this come from? So I skipped that step. I just went kind of fast. So I bring 100 over, and there's 145. So 45 feet is the driving head of this. Okay, so I've got this equation right there. So now if I take that friction factor, I can plug it in there. Okay. So 0.02, and I multiply that by that, and I divide that over into 45. Take the square root of that, and that tells me then my flow rate is, well, that's close enough to 6. I'm just going to call it 6 cubic feet per second. Okay. And now I can find the Reynolds number, right? We'll go back to the previous thing. The Reynolds number is 4 times Q times, no, it's 4Q divided by pi d times the viscosity. All right. So 4 times that, pi times d times the viscosity, 1.41, e to the negative 5. Write that in there, and I get a Reynolds number of 5.4 times 10 to the 5th. So now I have E over D, and I have the Reynolds number. So I can go to my equations, or I can go to the Moody diagram. A little far there, okay. So it's going to be in between these two right here, 3 zeros and 1 and 2. So I'm going to track that over here, and I'm going to come over to 5. What did I say that was? 5.4. So here's 10 to the 5th. There's 2. There's 4. There's 5. This is a log scale, so be careful. So it's going to be somewhere in there and somewhere down in here. So I'm going to guess that that's going to be about 0.0145. Okay. Okay. So now I would repeat the same thing. I would take this friction factor, stick that up to my equation right there, solve for the flow rate, take that flow rate, solve for the Reynolds number, and then take the new Reynolds number and my E over D into Moody and calculate my flow rate. I'm sorry, calculate my new friction factor. And you should find, even for wild guesses, that within 3 to 4 iterations, you are pretty much converged. If you're going 5 or 6, maybe ask yourself, what am I doing wrong? Maybe if it's a really wild guess, maybe 5. But if you're going 6, way too far. Once again, I punch this in, and you're going to find the next friction factor is going to be really, really close to that. And then we know what the flow rate is. So for 45-foot head differential, 1-foot pipe, same length, 4 feet gives us 6 cubic feet per second. So it's not quite 8, so I was a little bit off in my guess, but a lot closer than the other one. All right. So I'm out of time here, but I will post a couple of homework problems for you to try. They might be on conservation of mass as well, continuity equation, right? Just if we're running a flow through a 6-inch pipe and we jump up to an 8-inch pipe, how does the velocity change? That's pretty basic fluids. So I think you're good. So, Rachel? No, the homework will be due Wednesday.
Okay.
Yeah, the homework will be due Wednesday. So that way, over the long weekend, if you don't want to do the homework, you're more than welcome to wait till Tuesday to do it. So have a wonderful long weekend, and we will see you next Wednesday.
Thank you.
Yep.
Have a good weekend.
Thank you. You too.
Thank you.
You bet. We'll see you, Anthony.